On July 2nd, 2026, at exactly 4:30 in the afternoon local time, Indonesia's Geological Agency made a call that sent a ripple of alarm through the Sunda Strait. They raised the alert status of Anak Krakatau from level 2, known as waspada or caution, all the way up to level 3, known as siaga or alert. That is the second highest warning level Indonesia has on its books, just one step below a full eruption emergency. Within hours, officials had drawn a 3-kilometer exclusion zone around the crater and issued a blunt warning to fishermen, tourists, and climbers. Stay away, because pyroclastic flows, flying rock, and volcanic gas are now live threats, not hypothetical ones. This wasn't a guess. It wasn't a rumor spreading on social media. It was a formal, data-backed decision from the same agency that has been watching this mountain rise from the sea for nearly a century. And the data behind that decision is staggering. Between June 16th and July the 2nd alone, monitoring stations recorded 740 emission earthquakes, 24 harmonic tremors, 247 low-frequency earthquakes, and 520 hybrid earthquakes shaking the ground beneath this small volcanic island. Add to that 16 continuous tremor events, a handful of shallow and deep volcanic quakes, and tilt meters at 2 separate monitoring stations, picking up fluctuating ground deformation. This is not a mountain sitting quietly. This is a mountain in motion. To understand why this single volcano commands so much attention from scientists, governments, and ordinary people thousands of kilometers away, you have to go back nearly a century and a half to an event that still shapes how we think about natural disasters today. In August of 1883, the original Krakatoa erupted with a violence that is genuinely difficult to comprehend. The explosion was heard over 4,000 kilometers away, in places as distant as the interior of Australia and the island of Rodrigues near Madagascar. It remains one of the loudest sounds ever recorded in human history. The eruption column punched more than 25 kilometers into the sky. It triggered tsunamis that reached heights of over 30 meters in places, waves that scoured coastal villages along the Sunda Strait and killed somewhere in the range of 36,000 people, according to most historical estimates. Ash from the eruption circled the globe, cooling average temperatures for the following year and painting sunsets in eerie blood red as far away as London and New York. 2/3 of the original island collapsed into the sea during the eruption, leaving behind a submerged caldera and a scattering of remnant peaks. For decades afterward, the strait was quiet. The sea covered the wound. Then, in December of 1927, fishermen and local observers began noticing something strange. Steam and ash were rising from the water in the middle of the old caldera. A new volcanic cone was being born, quite literally from the crater of its predecessor. Indonesians and volcanologists alike gave it a name that captures exactly what it is, Anak Krakatau, which translates to child of Krakatoa. Over the following decades, this child grew the way volcanic islands do, through repeated cycles of eruption, lava flow, and ash deposition, each event adding another thin layer to its cone. By the 2010s, Anak Krakatau had grown to a height of well over 300 meters above sea level, an entire island built from scratch by the same volcanic system that had produced one of history's most catastrophic eruptions. Locals began running boat tours out to see it. It became something of a tourist attraction, a living demonstration of how new land is made. But volcanologists never stopped watching it closely because a volcano built rapidly out of loose, unconsolidated material carries a very specific kind of danger, one that doesn't require a massive eruption to become lethal. That danger revealed itself on December 22nd, 2018. Without the kind of days-long warning signs that usually precede a major eruption, the southwestern flank of Anak Krakatau collapsed into the sea. Roughly 2/3 of the volcano's above-water structure slid downward in a matter of minutes, sending an enormous volume of rock and volcanic debris crashing into the ocean. That collapse displaced massive amounts of water, generating a tsunami that raced across the Sunda Strait toward the coastlines of western Java and southern Sumatra. There had been no major earthquake to trigger tsunami warning systems, no seismic signal that conventional monitoring was built to catch. The wave arrived at beaches and coastal towns with almost no warning at all. 437 people were killed. Thousands more were injured, and tens of thousands were displaced from homes along the coast. It was, in a very real sense, a wake-up call for volcanic hazard science worldwide, because it demonstrated that a volcano doesn't need an explosive eruption to kill people at a distance. A structural collapse alone, driven by an island built on loose, weakly bonded volcanic material, can be enough. That history is exactly why the events of the past 2 months matter so much, and why headlines are once again asking whether this volcano is waking up. To be precise about the science here, Anak Krakatau never really went dormant after 2018. It has been erupting, on and off, essentially continuously since then, part of a long pattern of activity going back to its birth in 1927. What changed this summer wasn't the presence of activity, it was the intensity and character of that activity. Seismologists at the volcano's monitoring post in Hargopankuran noticed that starting around June 26th, the rate of what are called exhalation earthquakes, the small seismic events associated with gas and steam escaping the volcanic conduit, began climbing sharply. Ash-bearing plumes shifted from occasional wisps to consistent gray to black columns visible from the mainland. By July 1st, unrest activity had visibly increased, with ash and gas plumes rising as high as 200 meters above the vent. Then, on July 2nd, at 2:05 in the afternoon local time, the volcano produced an eruption that lasted around 20 seconds and sent a dense gray to black ash column roughly 200 meters into the sky, drifting toward the northwest. The event was captured on seismographs with a maximum amplitude of 23 millimeters, a number that might sound abstract, but to the trained eye of a volcanologist reading a seismogram indicates a genuinely energetic explosion for a volcano of this size. 90 minutes later, the Geological Agency made its announcement, moving the alert status to level 3 and drawing that 3-kilometer exclusion zone. From that point forward, the volcano did not quiet back down. Over the following 2 weeks, monitoring teams logged eruption after eruption. By July 11th, the tally for the period stretching back to June 2nd stood at 19 separate eruptive events. Ash plumes during the second week of July were regularly climbing between 100 and 400 meters above the summit, drifting in different directions depending on the day's winds, sometimes northwest, sometimes north, sometimes northeast. On the night of July 11th, observers on the monitoring post reported visible incandescence, meaning the glow of hot material at the crater was bright enough to be seen against the night sky, a visual sign that fresh magma is close enough to the surface to radiate heat and light. Throughout this period, the technical language coming out of the monitoring stations painted a consistent picture of a volcano under active internal pressure. Seismic monitoring on a single evening in early July, between 6 in the evening and midnight, recorded 14 distinct blast earthquakes, each with amplitudes between roughly 6 and 11 millimeters, and durations stretching from 20 to 46 seconds. On top of that, monitors logged 6 harmonic earthquakes, a type of rhythmic seismic signal often associated with the resonant movement of fluid or gas through underground channels, along with a continuous tremor event that persisted at low amplitude. None of these individual data points would necessarily alarm a scientist on their own. Volcanoes generate background seismicity all the time. What matters is the pattern, the trend, the way these signals stack together and shift over weeks. And in Anak Krakatau's case, virtually every category of seismic signal, gas emission indicator, and visual observation moved in the same direction at the same time, upward. Numbers like these can feel abstract when they're read off a page, so it helps to put them in context against what a genuinely quiet volcano looks like on the same instruments. A dormant or lightly active volcanic system might generate a handful of small earthquakes in a given week, background noise from a crust that is never truly still anywhere on Earth. Anak Krakatau, during this same stretch, was producing dozens of distinct seismic events per day across multiple categories, sustained over more than 2 weeks without a significant lull. That sustained character is, in many ways, more informative to a volcanologist than any single dramatic spike would be. A brief burst of seismicity followed by quiet often indicates a small, self-limiting release of pressure, gas escaping through an existing crack before things settle back down. A sustained multi-week pattern that keeps climbing across several independent measurement types at once, seismic counts, tremor duration, ash column height, and ground tilt, suggests something closer to an underlying system continuing to charge with pressure, even if the surface expression remains, for now, relatively modest. It's worth pausing here to explain, in plain terms, what these different signals actually mean, because understanding them is the difference between panic and informed awareness. When magma or volcanic gas tries to force its way toward the surface through cracks and conduits in solid rock, it generates vibrations. Different types of movement create different seismic signatures. Sharp, high-frequency earthquakes often indicate rock literally fracturing under stress, brittle failure as magma pushes new pathways open. Low-frequency and harmonic earthquakes, by contrast, tend to reflect the resonant vibration of fluids, whether that's magma, water, or gas, moving through those same pathways, similar in principle to the way air moving through an organ pipe produces a tone. Hybrid earthquakes combine characteristics of both, suggesting a mix of fracturing rock and moving fluid happening close together in time and space. Tremor, the continuous, sustained shaking rather than discrete quake events, usually points to sustained fluid movement, degassing, or, in more advanced stages, magma actively flowing near the surface. Ground deformation, tracked by tilt meters at stations with names like Kras, Lava 93, and Tanjung, measures whether the volcanic edifice itself is physically swelling or subsiding, a direct proxy for whether pressure is building underground. Indonesian scientists reported that the Tanjung station showed a pattern of fluctuating low-scale inflation this summer, which they explicitly linked to the elevated shallow seismicity when justifying the decision to raise the alert level. In other words, the ground was rising, just slightly, just enough to register on precision instruments, at the same time that shallow earthquakes were increasing. That combination, inflation plus shallow seismic swarm plus visible plume escalation, is close to the textbook definition of a volcano building toward more vigorous activity. None of this means scientists are predicting a repeat of 1883, and it's worth being very clear and very careful about that distinction, because it is easy for headlines and social media clips to blur the line between genuine unrest and imminent catastrophe. Indonesian volcanologists have been explicit that the current elevated activity, while serious enough to justify level 3 status and a hard exclusion zone, remains in a category that can be actively monitored and managed through mitigation measures. That is a meaningfully different situation from an uncontrolled, unpredictable crisis. The Geological Agency has also had to spend time publicly debunking hoax videos claiming far more dramatic eruptions than what instruments were actually recording. A reminder that misinformation tends to spread faster than verified data during any period of natural hazard uncertainty. The real story, grounded in the instrumental record, is one of a genuinely active, genuinely elevated volcanic system, being tracked in close to real time by a monitoring network built specifically because of the lessons learned in 2018. That monitoring network deserves its own explanation because it represents one of the more significant upgrades in disaster preparedness to come out of the 2018 tsunami tragedy. Before that event, Indonesia's tsunami warning systems were built almost entirely around detecting large offshore earthquakes, using seismographs and tidal gauges to catch the specific signature of a fault rupture. That system simply wasn't designed to catch a landslide-generated tsunami triggered by a volcanic flank collapse, because there was no large tectonic earthquake to detect in the first place. The wave that killed 437 people in 2018 arrived essentially without triggering any of the alarms built for that purpose. In the years since, Indonesian authorities, working alongside international volcanology and tsunami modeling researchers, have worked to build tsunami risk assessments specifically tailored to volcanic islands, incorporating continuous monitoring of ground deformation, real-time seismic tracking, and lessons drawn directly from satellite radar analysis of the 2018 collapse. That analysis, conducted after the fact, confirmed precisely what happened. A landslide originating on the volcano's southwestern flank displaced an enormous volume of seawater, generating a series of waves that struck the coastline with almost no lead time. It's important to say clearly that experts studying the current situation have stressed elevated ash emissions, increased seismicity, and a raised alert level do not, on their own, establish that another tsunami-generating collapse is imminent or even likely. Every eruption at Anak Krakatau is different. The volcano's construction, its slope stability, the volume and type of new material being added to the cone, all of these factors vary from one eruptive episode to the next, and history shows plenty of active periods that never produced a flank failure at all. But the 2018 event permanently changed how seriously any period of unrest at this particular volcano gets treated, because it proved that the worst-case scenario here doesn't look like most people's mental image of a volcanic disaster. It doesn't necessarily involve lava flows creeping toward villages or ash falling on distant cities. It can be sudden, silent, and delivered by the sea itself, striking coastlines that, in some cases, sit less than 50 kilometers from the volcano across open water. This is part of why the framing of Anak Krakatau as Asia's deadliest volcano carries real historical weight rather than being simple headline hyperbole. The death toll from the 1883 eruption remains, to this day, among the highest ever recorded from a single volcanic event anywhere on Earth, and the 2018 collapse added a fresh, modern reminder that the danger here never fully went away, it simply changes shape. Indonesia as a whole sits at the convergence of three major tectonic plates, part of the Pacific Ring of Fire, and hosts more active volcanoes than almost any other country on the planet. An estimated 8.5 million people live within just 10 kilometers of an active volcano somewhere in the Indonesian archipelago, a population density around dangerous terrain that has few parallels anywhere else in the world. Anak Krakatau itself sits uninhabited, a bare volcanic cone rising from the water, but the coastlines of Java and Sumatra that flank the Sunda Strait are home to dense populations, major ports, and, critically, the memory of what happened just a few years ago. Since the current elevation to level 3, local authorities in South Lampung, the regency on Sumatra's coast closest to the volcano, have repeated their warnings on what feels like a rolling, near-daily basis. Fishermen, tourists, and hikers have been told, in blunt terms, not to approach within 2 to 3 kilometers of the active crater. Local monitoring posts have continued reporting conditions multiple times per day, tracking not just eruptions, but the more subtle signals, gusts of gas escaping the crater, minor emission earthquakes, shifts in visibility as fog rolls over the summit. By mid-July, officials were describing the volcano's activity as still fluctuating, still requiring 24-hour monitoring, language that reflects genuine scientific caution rather than either complacency or alarmism. As of the middle of July, the Global Volcanism Program, jointly run by the Smithsonian Institution and the United States Geological Survey, was reporting continued eruption through the week of the 9th through the 15th, with white, gray, and black ash plumes reaching as high as 400 meters above the summit and drifting in varying directions depending on daily wind patterns. Incandescence, that visible glow of hot rock and fresh magma, continued to be observed at night through the middle of the month. Zooming out from Anak Krakatau specifically, this kind of volcanic reawakening is not happening in isolation. Across the broader region, and across the Pacific Ring of Fire more generally, 2026 has been a year in which multiple long-dormant or historically quiet volcanic systems have shown measurable signs of change. In Japan, Mount Fuji, which last erupted more than 3 centuries ago in 1707 and sits within roughly 100 kilometers of Greater Tokyo, one of the most densely populated metropolitan regions on the planet, experienced an uplift episode on its northern caldera rim beginning in the middle of 2025. Deformation monitoring through the start of 2026 has shown that uplift largely stabilizing since January, but geologists have continued watching closely, precisely because Fuji's proximity to tens of millions of people means even subtle changes warrant sustained attention. In the Philippines, Taal Volcano, a volcano contained within a lake that itself sits inside an ancient caldera south of Manila, continues emitting well over 1,000 tons of sulfur dioxide gas daily as of this year, a persistent reminder that Taal, responsible for more than 6,000 deaths across its documented eruption history, remains an active hazard even during periods without dramatic eruptive events. Indonesia's Mount Dukono, a volcano that has been erupting essentially continuously since 1933, made international headlines earlier this year for a tragic reason. In May, 3 hikers, 2 from Singapore and 1 Indonesian, were killed after their guide led them into an active exclusion zone that had been established weeks earlier by Indonesian volcanic monitoring authorities. That incident, distinct from the current Anak Krakatau situation, but part of the same broader pattern of elevated regional volcanic activity, serves as a sobering illustration of what happens when official warnings and exclusion zones are ignored, whether out of unawareness or simple disregard for posted danger. There is also a satellite dimension to this story that rarely makes it into casual conversation, but plays an increasingly central role in how agencies verify what's happening on the ground. Throughout the period of escalating unrest, satellite imagery from missions like the European Union's Copernicus Sentinel-2 program captured direct visual confirmation of active plumes rising from the crater. Imagery that let researchers and the public alike see, from orbit, exactly what the ground-based instruments were describing in numerical terms. This kind of satellite corroboration matters enormously for a volcano sitting on an uninhabited island in the middle of a strait, where placing extensive ground-based observation equipment directly on the crater itself is neither safe nor practical. Darwin's Volcanic Ash Advisory Center, the regional authority responsible for tracking ash clouds that could threaten aviation across Southeast Asia and the surrounding oceanic airspace, issued a string of advisories through late June and early July, tracking plumes as they drifted west-northwest and west-southwest across the strait, information that gets fed directly to airlines routing flights through the region. Volcanic ash, even in relatively modest quantities, poses a serious hazard to jet engines, and this kind of continuous advisory tracking represents another layer of the modern monitoring apparatus, built specifically because volcanic hazards don't stop at the shoreline or stay confined to the exclusion zone drawn on a map. Scientists studying this broader pattern of reawakening volcanoes have pointed out that the tools used to monitor these systems, tracking gas emissions, mapping ground deformation, cataloging volcano-tectonic earthquakes, and even measuring subtle gravity anomalies that can reveal underground magma movement, are increasingly capable of detecting unrest in volcanoes that had previously been written off as extinct or permanently dormant. A geological survey published this year covering the Methana volcano near Athens, Greece, mapped 700,000 years of eruptive history and found a pattern of long, quiet intervals punctuated by renewed activity, a pattern the researchers argued challenges the entire concept of a truly extinct volcano. Their broader point, one echoed by volcanologists studying Anak Krakatau and dozens of other systems worldwide, is that with enough historical data and precise enough modern instrumentation, global hazard authorities are getting better at identifying which long-slumbering volcanoes are quietly stirring back to life, long before that activity becomes visible to the naked eye or dramatic enough to make headlines on its own. That improving science comes with an important and honest caveat, one that responsible volcanologists repeat constantly and that deserves emphasis here rather than being glossed over for the sake of a cleaner narrative. Detecting unrest is not the same thing as predicting an eruption's timing or scale. Even with dense networks of seismographs, tilt meters, gas sensors, and satellite radar, the relationship between rising seismicity, ground deformation, and an eventual eruption remains genuinely difficult to model with precision, because every volcano is built differently from different rock, under different stress conditions, with a different history of prior eruptions shaping its internal plumbing. Some volcanoes give months of escalating warning signs before finally erupting. Others, like Anak Krakatau's 2018 flank collapse, can shift from apparently stable to catastrophic within minutes, without ever producing the kind of extended seismic buildup that instruments are best at catching. This uncertainty isn't a failure of the science. It's an honest reflection of how genuinely chaotic and locally specific volcanic systems are, and it's exactly why agencies like Indonesia's Geological Agency lean toward conservative, precautionary alert levels and exclusion zones, rather than waiting for perfect certainty before acting. Raising the alert to level 3 doesn't mean scientists know an eruption is coming in a specific window of days or weeks. It means the underlying data has crossed a threshold where the risk to human life justifies restricting access and increasing surveillance, a judgment built on decades of accumulated experience watching how this particular volcano, and volcanoes like it, tend to behave once they start showing this combination of signals. For the communities living along the Sunda Strait, this translates into a very specific, very practical kind of daily vigilance rather than any sense of imminent doom. Coastal towns in South Lampung and along the western Java coast have, since 2018, incorporated volcanic tsunami risk into their broader disaster preparedness planning, alongside the more familiar earthquake and seismic tsunami risks that have long shaped emergency planning across the Indonesian archipelago. Evacuation routes, early warning communication systems, and public education campaigns about recognizing the signs of an approaching wave, unusual sea recession, unexplained ground shaking, sudden roaring sounds from the water, have all been strengthened in the years since the tragedy. Local fishing communities, many of whom depend on waters close to the volcano for their livelihoods, have had to internalize a new set of boundaries, staying the recommended 2 to 3 kilometers clear of the crater even during periods when the volcano appears visually calm, because the visual state of a volcano and its underlying seismic state are not always the same thing. Beyond the immediate coastline, there's a longer historical thread worth drawing out, because it reframes how we should think about a single summer of elevated seismicity against the deeper timescale on which this volcanic system actually operates. Geological surveys of the Krakatau caldera complex show a documented eruption history stretching back centuries before the famous 1883 event, with recorded activity in the 1500s, the 1680s, and periodically throughout the following 2 centuries. After 1883 essentially reset the system by collapsing the original island, the newborn Anak Krakatau went on to erupt in some form during nearly every decade of the 20th century, from the 1930s through the 1950s, 60s, 70s, 80s, and 90s, right through to the string of 21st century episodes that culminated in the 2018 collapse and have continued in various forms ever since. Viewed against that full record, the current bout of elevated activity isn't an aberration or freak occurrence. It's simply the latest entry in an extremely long, extremely consistent pattern of a volcanic system that essentially never stops building, venting, and occasionally violently reorganizing itself. What makes each individual episode worth tracking closely isn't novelty. It's the simple fact that somewhere in that long, repetitive pattern sits the next flank collapse, the next major explosive phase, or perhaps just another few months of modest ash plumes that eventually settle back toward baseline, and there is currently no way to know in advance which of those outcomes this particular episode will turn out to be. There's also a broader economic and social dimension worth acknowledging, honestly. Anak Krakatau had, in the years before 2018, and even to some degree afterward, become something of a niche tourist draw. Boat operators running day trips out from Java or Sumatra to let visitors see an actively growing volcanic island up close, sometimes even landing briefly on its slopes during periods of lower activity. That kind of tourism carries obvious risk that became tragically clear in 2018 when the flank collapse and resulting tsunami struck without the kind of extended warning that would have allowed evacuation. The current level 3 status and its accompanying exclusion zone effectively shuts down that activity for the duration of the elevated alert, a real economic impact on local boat operators and guides, but one that regional authorities and most independent volcanologists agree is the responsible trade-off given what's at stake. The Mount Tukono tragedy earlier this year, where a guide led paying tourists into a zone that had been under an active exclusion order since April, stands as a stark, recent example of what can happen when that trade-off gets ignored, whether through unawareness of posted warnings or willingness to accept risk on behalf of paying customers who may not fully understand what they've signed up for. As July gave way to the final days of the month, Anak Krakatau's status remained unchanged, level 3, Siaga, with the 3-kilometer exclusion zone still firmly in place. Eruptions continued at an irregular but persistent pace. Gas and ash plumes rising in generally modest but consistent bursts of 50 to 400 meters above the vent. Seismic stations continuing to log the steady background hum of emission quakes, tremor, and occasional harmonic signals. This pattern, an active but not dramatically escalating volcano, sustained over weeks rather than resolving quickly in either direction, is in some ways the most common and least headline-friendly reality of volcanic monitoring. Most periods of elevated volcanic unrest don't resolve into either a dramatic eruption or a quick return to calm. They persist, sometimes for months, sometimes for years, as background conditions that require ongoing vigilance without producing a single decisive event that neatly closes the story. What makes this particular episode worth understanding in detail isn't that it represents a uniquely unprecedented crisis, because by most technical measures, this is a serious but manageable period of elevated activity at a volcano that has, in one form or another, been active almost continuously since its birth nearly a century ago. What makes it worth understanding is what it represents. A live, ongoing case study in how modern volcanology actually works. How scientists translate raw instrumental data, earthquake counts, tremor amplitudes, tilt measurements, into public safety decisions that affect the lives of millions of people living along one of the world's most volcanically active coastlines. It's also a reminder that the history written into the geology of a place doesn't disappear just because a few decades pass quietly. The same tectonic forces that produced the deadliest single volcanic eruption in recorded history in 1883 never stopped operating beneath the Sunda Strait. They simply kept building, cone by cone, ash layer by ash layer, earthquake by earthquake, into the volcano now sitting at level 3 alert, as monitoring teams watch around the clock. Whether the current unrest at Anak Krakatau eventually escalates into something more dramatic, gradually subsides back toward baseline activity, or simply continues at its present fluctuating pace, for the foreseeable future is, honestly, something no scientist can say with certainty today. What can be said with confidence is that the instruments are running, the monitoring posts are staffed around the clock, the exclusion zones are enforced, and the lessons of 2018 have visibly reshaped how seriously this particular kind of unrest gets treated by the people whose job it is to watch this mountain. For millions of people living along the Sunda Strait's coastlines, and for the broader scientific community tracking volcanic reawakenings from Japan to Alaska to Greece this year, Anak Krakatau stands as perhaps the clearest reminder available right now that some of the most consequential geological forces on Earth operate on timescales and through mechanisms that modern science can detect, measure, and respond to, even if it still can't predict them with perfect precision. There's a certain irony worth sitting with as this story continues to unfold in real time. The very name given to this volcano back in 1927, Child of Krakatoa, was meant to describe a birth, a small cone rising from the drowned caldera of its parent. Nearly 100 years later, that child has grown into a volcano fully capable of producing its own chapter in the region's long, difficult relationship with the ground beneath it, one written in exhalation earthquakes, tilt-meter graphs, and 3-kilometer exclusion zones, rather than in the single catastrophic afternoon that ended its parent's original form. For the scientists watching seismographs update in real time from monitoring posts along the Lampung coast, for the fishermen adjusting their routes to stay clear of the crater, and for coastal communities who still remember the last week of December 2018, the current elevated status of Anak Krakatau is neither a false alarm nor confirmation of impending catastrophe. It's simply the latest, closely measured chapter in the ongoing story of a volcano that has never really stopped writing itself into existence. One eruption, one earthquake swarm, and one carefully issued alert level at a time. The child of Krakatoa, born from the ashes of history's most infamous eruption, is once again reminding the world that it never really went to sleep. It was simply waiting, the way volcanoes do, for the pressure underneath to build again.